So we just have to do the math right to get it close. But if you put an equation like this, you're 9 out of 10 points of the way there. You just have to plug the values in your calculator. Yeah?
Why is it not final mass initial for temperature?
Ah, okay. So is this quantity going to be positive or negative? Positive, right? And so if you put in final minus initial here, you're going to get your sign goofed up. Because what temperature is higher? The initial temperature of the iron or the final temperature of the iron? Initial, right? So the initial temperature we know is greater than the final temperature. And so you need to make sure to get your signs right. If you have final minus initial, this is going to be negative, this is going to be positive, it's not going to work out very well. And you can sort of ballpark that because I think if you solve it one way, you get about 106C or 107C. I can't remember exactly what the answer is. If you try and solve it the other way, you get all goofed up. And so you need to think, okay, I know that the initial temperature is going to be higher than the final temperature, so when I solve this equation, I need to make sure that it works out. It's not going to be lower, right?
Does anyone in here have the exact answer to that question?
I do. I mean, I just have to look it up on my computer. Whose exam was this? So the exact answer to that...
I have 330 degrees.
Oh, it is? Okay, it's that high. Hold on. I'll tell you what I got. Oh, I don't have it because I don't have an electronic copy of it. If you want to email me tonight, just to remind me, I'll email it out to the whole class. Yeah.
When you say Q of iron equals Q of H2O, is one of them going to be negative?
So depending on, well, no. So my advice is to make them both positive. But you know in your diagram, right? When Q is going one way versus when Q is going the other way between system and surroundings, you've got positive and negatives that you need to account for because the internal energy is going up and down. However, this is, if you make the absolute value equal in these types of problems, you can't go wrong. Yeah.
Because what I had mine, I had the cubed water and I found that one was, and then I put a negative sign in front of it because the iron is losing that Q, and then it still works with temperature final minus temperature.
Yeah. So if you do make this one negative, or if you make one side negative, then you can do T final minus T initial. Yeah. So let's just find the answer. Since we're all wondering what the answer is. Does anyone have a calculator? Oh, okay. What's the answer?
367.5.
T initial is 367.5 what? Degrees C. So you get that by 1,000 times 4.185 times 12.8 divided by, let's see, 400 times 0.45 minus 32.8. So that should equal 376.5. Is that right? Yeah. So if that's not right, let me know, but I think that's the answer. Or maybe it's plus. Maybe it's plus, sorry. There we go. T initial minus T final, so it's plus. Other questions? So yeah, so the important part of this calorimetry thing is what's calorimeter doing? What's heat capacity about? You know, how does the heat flows work? How do you calculate what the heat is, you know, for your water phase or your iron? You know, is the temperature going to go up or down? That stuff's important. So the conceptual parts of the calorimeter. Other questions? Yeah.
Number 8, do you want me to just read it to you?
Oh, let me see.
It's a conceptual one.
Oh,
Dismissed
okay.
it.
Number 8, an exothermic reaction is performed in a perfectly insulated, perfectly rigid box. I remember this one. So we perform a reaction in there and we have a perfectly insulated box. What does insulated mean?
Nothing can transfer.
You can't get out and you can't get in. So nothing is allowed across that boundary. Exothermic reaction is performed in a perfectly insulated, perfectly rigid box. Does the internal energy increase, decrease, or stay the same? Stays the same. Why does it stay the same?
No transfer.
Q and W are not allowed across that boundary because the box, of course, is perfectly rigid. Now, what if I told you that the box could expand? Then work could be done, right? And so you'd have to figure out if work is being done by the system or is work being done to the system. So if the box expands, work is being done by the system to the surroundings. And so work is transferred across that boundary. And remember your sign, so this will be important to have. Oh, I just saw it. No, that's not going to work. Remember this diagram, and so you really want to remember that W and Q leaving the system, going to surroundings is negative, and Q coming in or W coming in is positive. Why do we care? What's special about Q and W? What does their sum equal? Delta E is Q plus W. Is this voltage? No, it's internal energy. So what's the units of Q? Joules. What's the units of W? What's the units of delta E? Great. So in this case, if we allow this box to expand, what's the sign of W? Negative. Work is transferred from the system to the surroundings. What's the sign of delta E? Internal energy goes down, right? So the only way we can change the internal energy is if we transfer Q or W. And so that's what that whole question is about. Since this border is perfectly insulated, you can't exchange, and perfectly rigid, you can't exchange any Q or W. And so this is 0, this is 0, so delta E is 0. Even though the temperature inside the box goes up, right? Has to. It's an exothermic reaction, but that heat and work can't be transferred, and so delta E is 0. Yeah?
So if we deal with a rigid box, we always assume the inside's the system, the outside's the surroundings.
Yeah, so if I ask you about a box, usually the system is inside the box and the surroundings is outside the box. Or if I ask you about a house, the system is the house and the surroundings is the outside, right? Are you cool with that question now? Yeah? Make sure you know this will be important. So how does the internal energy change? What does the transfer of heat and work look like? Any other questions? Okay, I will see you on Tuesday. Yeah.
The equilibrium constant for a slightly soluble salt, what's the good range for that?
Yeah, so something like 10 to the minus 4, 10 to the minus 6, 10 to the minus 10 for slightly soluble. So Q is concentration of products over concentration of reactants. So for something that's slightly soluble, like calcium carbonate, gonna go to Ca2 plus carbonate 2 minus. These concentrations are going to be very small, right? And so K dissolution is going to be small because you don't have many ions, right? Slightly soluble. Yes?
Number 2.
Number 2. The following reaction is given for dissolution. Okay, if a strong acid fully dissociates in water, okay. So this is the exact opposite of this question that I just answered. So let's do it. Strong acid. What does the strong acid mean?
High
Low-
concentration H plus.
High concentration, high dissociation, right? So what's the Q for this reaction? Right? Water doesn't go in there because that concentration is considered 1.